This lecture is especially for the student of plus 2, and we'll discuss about the topic electrostat. Basically, we'll divide this particular topic into three part. That is, number one, electric field and potential, then Gauss's theorem and its application, and then finally capacitor. So we'll start with the first topic, that is electric field and potential. Now from this particular, or as far related to this particular topic, we'll start with charge. The first term which comes in our mind is, what is charge? Moving on to charge, before that, before discussing charge, we should understand what is electrostatic, or what actually does it mean. So like when we talk about electrostatistics, statics, it's made up of two words, electron and static. So when the electron is at rest, static means rest. So when electron is at rest, so what property will it have, and what will be this application, the properties is with it. So all such thing will be dealt in this particular broader topic, that is electrostatistics. Again, as far as charge, which is an most important aspect of electrostat, charge basically is associated with electron, and this charge, it can further be divided into either positive or negative. So when we talk about the charge related to electrostat, we talk about the electron, the excess of electron means negative. Deficiency of electron means positive. So this is what you understand. So that's an excess of electron is negative, and a deficiency of electron is positive. Now charge basically is quantized. What we know is that charge is quantized. So quantized means it may not exist in an say in a fraction or something like that. Rather, it will be available in an integral form. So it will be something like this, plus minus Ne. The smallest unit, or the smallest magnitude or value of the charge is 1.6 into 10 to the power minus 19 coulomb. So this is the smallest unit. So when you say that a unit of a charge, it simply means 1.6 into 10 to the power minus 19 coulomb. Right. Now, as far as charge, the property of charge is concerned, we know that like charges repel and unlike charges. So that is the broader idea which you'll have. Now, again moving on to the next topic related to this field and potential chapter. The most important one is the Coulomb's law. Coulomb's law of electrostat. And it simply means that if we have two charges, Q1 and Q2, and the force, and if there is the distance r is between them, then the force will be directly proportional to the product of the charge and inversely proportional to the square of the distance between these two charges. So combining these two, will have Q1 Q2 by r square, or F is equal to K Q1 Q2 by r square. The value of K is 1 by 4 pi epsilon naught for space. Now this is what we know. So obviously, if Q1 and Q2 is positive, then this force will be repulsive. Again, if Q1 and Q2 both are negative, again it will be repulsive. But if these two charges are of opposite nature, then the force will be attractive one. Now this is a very basic fundamental law related with Coulomb's law. Here the value of epsilon naught is given by 8.85 into 10 to the power minus 12. Okay. Um, Coulomb square, Newton depth square. So this is the value of epsilon naught, and the value of K is 9 into 10 to the power 9 Newton meter square by Coulomb square. So this is the value of K, which the student of +2 should have an idea about, or they must know this thing. So this basic lecture is for the beginner, for the student of +2 who have just entered into +2, and this will be the first chapter which they will read. So I think this is the basic fundamental one. Again, we can move on to the next one, next topic, which is the potential. So basically, what is electric potential? Okay. So next is potential, or rather electric potential. It is denoted by V. Okay. So it is the amount of work done in moving a charge, moving a unit charge rather, from unity to that point. Okay. Now this is what the definition of V is all about. Now one more thing is there, that is electric potential energy. Electric potential energy, which is denoted by U. Okay. So the relation between U and V is given by U is equal to Q into V. How to find U? Now to get U, we will consider a charge, a fixed charge. Okay. And there is a unit, another charge Q. The distance between this is R. So the force between these two is given by 1 by 4 pi epsilon naught capital Q to small q by R square. Now what we know is like the work done, rather, VW is given by F dr. So 1 by 4 pi epsilon naught capital Q small q by R square into dr. So we just assume that this is the elementary displacement. Okay, dr is the elementary displacement and dw is the small amount of work done in the process. So dw is equal to this much. Integrating this one, we will get 1 by 4 pi epsilon naught q into capital Q will be the constant term, so it will come out and it may be integrated, say, from R1 to R2. So W is equal to, this integration will give you 1 by 4 pi epsilon naught capital Q into small q minus 1 by R, R1 to R2. So, so I can tell that W is equal to 1 by 4 pi epsilon naught capital Q into small q. The value of this is minus to the minus outside, so 1 by R2 minus 1 by R1. Now if we put the minus sign inside it, we get 1 by 4 pi epsilon naught 1 by R1 minus 1 by R2. So this work done will be stored as an energy in it, potential energy rather, and it will be given by 1 by R1 minus 1 by R2. The relation between this potential energy and work done is that it's a negative of the work done. If we put R1 as R1 from infinity, so if R1 is infinity, R1 tends to infinity and R2 tends to R, we get U is equal to capital Q by capital Q small q by 4 pi epsilon naught, and it will be something like this. So capital Q to small q by 4 pi epsilon naught R will give you the value of small u. Now U, V is equal to, what we know so far is U is equal to QV. So Q, that is small q, and v will be now 4 pi epsilon naught r. So ultimately v will be equal to capital Q by 4 pi epsilon naught to r. So this will be the expression for v. So we'll just stop here. In the next chapter we'll continue from here onward. Okay, thank you very much.